Testing 1, 2, 3. Good afternoon, YouTube. Coming at you live from New York City. It's gotten awfully dark. I think it's ready to pour out. So my name is Greg. I'm from GregsTutoringNYC at gmail.com. I do a lot of videos about a lot of stuff. I tutor a lot of kids about a lot of stuff. I mainly specialize in specialized tests. So things like the PSAT and the New York State tests. I also specialize in things like, okay, great, Leo. I also specialize in things like the SHSAT, the PSAT, a whole bunch of other specialized tests like the CHSEE, the Catholic High School test, the Hunter College High School test, the Bergen County Academy tests, the Beacon Baccalaureate tests, the ISEE, the SSAT. So there's a lot of overlap on them, and very often a whole bunch of common topics come up. One that's on a lot of these tests is GCF and LCM, which is the greatest common factor and the least common multiple. So I'm more or less just going to focus on the rawness of those two right now in this stream. I'm not sure how long this is going to go for because I actually haven't taught this topic in a really long time. I've tutored it to kids, but I'm going to try to kind of back off to it all and kind of cover a whole bunch of stuff about it. So hopefully we can do this in one swoop, hopefully in about 45 minutes. I have free time, so I'm willing to go about an hour and a half on this. But I actually hope it doesn't take an hour and a half. But let's see. Let's see where we explore stuff. Again, I'm Greg from GregsTutoringNYC at gmail.com. If anybody has any questions, you can always email me. I'm freely available. Please check out my other videos. Please like this video. Please subscribe to my channel. I'll be doing a ton of stuff. So let me move me over to the side, and let's get dirty here. All right, my phone is oriented the right way. We don't need any other documentation here except for my screen. So this is greatest common factor and least common multiple. So we're going to be focusing on factors and multiples. And these two terms are often used to solve some similar problems. There's also kids confused about which is which. Okay? I think the key is remembering the last word of each of these. Okay? So this means common. There's two lists of things we're going to end up having. What's common across the two lists? In one case, we're looking for multiples that are common. In the other cases, we're looking for factors that are common. In this one, we're looking for the largest factor that's common. In this one gets a little misinterpreted because it says the least common multiple. And that almost sounds like it's a frequency problem. It's saying out of all the common multiples, which is the least one? So there's different sets of problems that support either one of these. By the way, I believe in Britain, this is called the HCF, the highest common factor. So there's lots of things that may say this. We don't seem to use this in the United States, or at least I'm not familiar with it. It's happening. LCM is, I think when I was a boy, I learned it as LCD, which is the least common denominator. And this is a case where you use it often. If I have something like a third plus a fourth, I really want to get those in twelfths. X and Y this is going to be. So the question is, how do we decide which denominator to use? So there's a couple ways to do it, and they all work. But one way is to get the least common multiple of these two numbers. In this case, it would be 12. All right, so what we'll do is try to beat this to death slightly. So let's talk about what is a factor. Let's just make sure the stream is going. Yeah, I think we're going okay. So a factor is a number that when multiplied by another number equals some product. So when we multiply two things, we get a product. So a factor is an integer right? It's a whole number multiplied by another whole number gives the product. Okay, so that's normally what we're talking about factors. We're not talking about 0.25 times 0.25 equals something. We're talking about whole numbers. So that we've had a product. If we have a product, how can we split it back into these two other pieces? That's really what we're talking about here with factors. So an example is the factors of 2 is 1 and 2. Each of these we can multiply to get that. A factors of 4 is 1, 2, and 4. We can talk about how to bounce through that, and we'll go through an example of how to do that. But these are the factors of 4. I can do 1 times 4 or 2 times 2. I can get the factors. So we're trying to do terminology in a second. The others, we go back to the LCM. This is a multiple. So if I have 2, a multiple of 2 is 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6. 2 times 4 is 8. These are multiples of 2. I'm going to put x2. Multiples of 2, 2, 4, 6, 8. Okay, these might also be factors for the other numbers. And some of the factors in the example up here might be multiples of other numbers. But don't confuse the two. They have different meanings and therefore different stuff. Certain problems require multiples. Okay, like the least common denominator might. That's how we got to 12. 12 was a multiple of 3. And 12 was also a multiple of 4. Okay, so we need to get that straight. Everybody's cool on terminology. What a factor is? Factor is an integer that we multiply by another integer to get a product. Once we have a product, we can rip it into other parts. A whole bunch of factors. Multiples is magnitudes of a number. 100%, 200%, 300%, 400%. Depends. There's a couple of ways to say what's happening here. Okay, and we can also talk about multiples. We can also have a multiple of something like 1.5. So 2 times 1.5 gets 3. Okay, we're not really talking about that when we do the LCM. We're really still talking about whole numbers. Okay, we can still figure out new calculations based on non-integer multipliers, but for now we're just going to concentrate on integer ones. Okay, positive numbers or negative numbers, and in some cases 0. Oh, in the case of 0, if I have something over 0, that's undefined. So we're not going to delve into that category because that's a pathological case. All right. So I put a bunch of notes here. Let me just jump into some of this. So let's get some factors down on a page. So I already gave 4. So we have 1, 2, and 4. So let's do something like what do I have here? 18. So what I like to do is just start from 1, and then on the other side, the matching factor, that's a factor pair, is 1 and 18. And then I start for 2. Does 2 work? Yes. And the other one is 9. Okay? Does 3 work? Yes. The other one is 6. Does 4 work? No. Does 5 work? No. Does 6 work? Yeah, we already covered. So we're done with 18. So we've gotten the factors. Here's another way to get factors. I'm just trying to make sure everybody's on the same page about what some of these things are. So if we did 24, we get 1, 24, 2, 12, 3, 8, 4, and 6. Okay? And if we have something like 51, which is why it's important to know how all your multiplications, we're going to start the same way, 1 and 51. 2, it's not even. 3, if the sum of the digits of this number adds up to a multiplier of that, is there like a fast way to solve LCM? Yeah, we're going to get there. We're going to get there. Because I'm more confused than GCF. For LCM, it looks like a SHSAT. You like the prime factorization. Yeah, you know what? It's a judgment call. We'll get there. It's probably going to take half an hour to get there. All right? Because really what it comes down to is if you have a simple number like 4, don't use the prime factorization. But if you have a more involved number like 24, there's a lot going on there. So in that case, you probably want to use that. So you have to do an on-the-fly assessment to see how nasty the number is or not. Because some numbers have a small factor families, and some have large factor families. For instance, this is a case like this. 51 looks nasty, but it's actually not. Because it turns out 2 doesn't go and 3 actually does. Okay, and the other corresponding one we get is 17. And it turns out there's nothing in the middle here. That's the 4 factors. So you can spend a lot of time trying to rip this apart, whether you do it this way or with the prime factorization tree. Okay, so it's a judgment call you have to run through. And by the way, I pointed out a few times to get familiar in a lot of my YouTubes here that there's numbers like 3 times 16, 3 times 17, 3 times 18. That's come up again here. And they're going to use a number like 51 or a multiple of 51, like times 3. They might use 153, which is 51 times 3. And you have to figure out at some point that 17 comes into play here. So the more familiar we get with common things. This is kind of like when you have a right triangle and there's a 3, 4, 5 right triangle. You just need to know that. This is going to come up on your test, for sure. For sure. Okay? So something like this is most likely going to come up. Same when I told you guys about x squared. Know your squares from 1 to 20. Because that's going to come up on some of these as well. All right? All right, so so to compute the greatest common factor, what we're going to do is create some of these lists. In other words, if we wanted to compare 4 and 18, we're going to look through the 2 lists and see of all the factors, which is the greatest one. So you might as well start from 4, because there's only 1, 2, and 4 here. And if we're going to compare 4 and 18, go backwards and see what you get. You don't get a 4, but you get a 2. So the 2 matches between 4 and 18, you're going to get a 2. All right? And between 18 and 24, you're going to do the same thing. Do we have an 18? No. Do we have a 9? No. Do we have a 6? Yes. So between 18 and 24, we're going to get a 6. Okay? And if I have between 24 and 51, 51 no, 17 no, we end up getting a 3. So the greatest common factor between 24 and 51 is 3. Now, since we're talking about GCF, which is factors, the factor is always going to be a smaller number than the numbers you're comparing. Right? With the least common multiple, the multiple is either going to be 100% equal to one of the numbers you're using or greater than it. Right? So that's kind of one thing you can use to try to maybe figure out which one you're supposed to be doing or not. Or if you get an answer saying like, whoa, wait a second. So in other words, if we got his greatest common factor between these two and got 99 between 24 and 51, let's say 99 was one of the factors, it doesn't make sense because it's greater than the both of these. All right? All right, so I have a bunch of notes here. I just covered a whole bunch of it. So let me see here. Also GCF is called greatest common divisor. So we had this up over here. Greatest common factor, highest common factor. It's also called the greatest common divisor as well in some context. Which is not to be confused with the least common denominator. I guess we could argue we could get the greatest common denominator as well. But normally you're not trying to do that. Normally you're trying to get the least common denominator. Okay? So we have some of these written out already. All right, so let me see here what I also have written down. All right, so that's some of the examples. There's an alternate way to do this, and let me get a blank piece of paper. So if we run through some of the same numbers, if we write the number, we're going to create a factor tree. Okay, so let's just start splitting this apart. Okay, so we're going to write 2 and 2 here. That means 2 times 2 is 4. If I had 8, and you could start anywhere on this, it doesn't matter. Okay, I'm going to have 2 times 4, and I'm going to split 4 into 2 times 2. And we can run through, when you get at the leaves, which is all the bottoms here, 2 times 2 is 4, and 2 times 2 times 2, we get 4 times 2 is 8. So we can always run through this to make sure we did it right. Okay? So what happens is when you use this scheme to get the factors, that's different than the thing before where I had the number, and we went 1 and then some number over here. We did x and we did a number here. And we went back and forth getting factor pairs. This is not getting factor pairs. This is called the factor tree. So what happens is when we spell out the factor tree, and by spelling I mean getting at the leaves here, as we spell it out, we're going to get a list of prime numbers at the end. Okay? So for instance, if we use 18, and by the way, we don't care about 1 in the number. And by the way, 1 is not a prime number. So that's why we're not going to use it either. So we're basically going to start from 2, or just figure out what's any divisor of the number. We don't care any divisor, and just start creating this. And as we go through with the two factors, we're going to split the factors down and down and down. So we're going to keep drilling down till we only get prime numbers at the end, and nothing else can be factorized. Okay? So if we get 18, we're going to get 2 and 9. Okay? And this is the same as 3 and 3. And we're done. There's nothing else more to do. And just to show you that you could use something else, we could have decided, oh, 3 and 6. Well, 6 is the same as 2 and 3. So we get 1, 2, and 2 3s. This is 2 times 3 times 3. And this ends up being 3 times 2 times 3. And if we order it, we get 2 times 3 times 3 as well. All right, so we can see they're both the same. So it doesn't matter which order we create the trees. Okay, this is called prime factorization. Okay, there's other ways to do prime factorization, by the way. But this is one way graphically, and there's multiple ways doing it graphically. I don't even want to get into the others. Just stick with this. It's quick. And as Leo's pointing out, if anybody's reading the comments, he's talking about what's the fastest way to solve something. So when you're on a test, right, we don't have the opportunity to write a computer program to do this. We don't have an opportunity to do it on our heads. Coming up with a list of factors like we had over here. Where is that? Up 24. Most people can't rip this apart in their head and memorize it. Your short-term memory is not good enough for that. Normally, we might be able to get 3 or 4 numbers, sometimes 7, which is why telephone numbers become handy. Is prime factorization better or the step method? Neither's better or worse. It's just if you have a clock going against you, I would go with prime factorization unless it's a simple number like 4 or 51. And of course, to get 51, you have to know the rule of 17 times 3 and so on. Otherwise, you're screwed. If you have no notion that this is a multiple 3, which gives you the 17, then you have to figure that out. And by the way, I pointed out in a lot of videos, I meant to say this earlier, and I answered your other question. 5 plus 1 is 6. That means this number, if we add up the sum of its digits, it's divisible by 3. There's also other numbers like 99. That's divisible by 3 because that's equal to 18, and we can reapply the rule. So 9 plus 9 is 18, we reapply it, and we get 9. 3 is divisible by 9. Well, it turns out it's divisible by 9 as well by the same rule. Okay? Well, first of all, we know it's 11. But if we add up its digits, and we can also divide that by 9. By the way, we can, if you know at any step along the way that it's divisible by 3, then it is. If you know at any step along the way that's divisible by 9, you also know it is. So you know it's 11 here, you know it's 2 here, and you know it's 1 here. So the division by 3 rules and the division by 9 rules are the same, except the sum of the digits have to add up to 3, or the sum of the digits have to add up to 9. And again, you can keep down the path, or you can divide it with no remainder along the way. So 9 is another gotcha one, because most people don't know the 9 times table. It's a sloppy one. Okay, especially if it's something like 9 times 25 or something like that. That gets nasty. So if you had that answer, which is 180 plus 45, so you get 5, 2, you get 225. If I just gave you 225, if I did that right, let's assume I did, most people can't figure out in their head or just know with the snap of the fingers that that's divisible by 9. So this is the quandary and which way to choose. Okay? All right? One of the things I don't like about this list is it's dependent on you. If you happen to skip one, then that's the end of that factor pair. If for some reason you forget 4 and 6, then that's the end of that here. But if you did a factor tree for 24, you have to keep going. So again, it doesn't matter where we start. But we do, let's say we do 6 and 4. This is going to split up to 2 and 3. If we stop here, we see 4 still needs to be completed. This becomes 2 and 2. And we can work backwards. 6 times 2 is 12, times 2 is 24. So we have a way to double check this. And this is pretty reasonable. It's balanced. Okay, we could also done it the other way, which is we get 2 and 12. 12 becomes 2 and 6. 6 becomes 2 and 3. So it depends how we do it. The other side of the coin is on something like the SHSAT, they're not going to give you a number like 9999. That's just too huge, unless there's something obvious about this number, like it's 1001. You probably know there's no other factors there. That's probably a prime number. Okay? Most likely it is. So unless you can conclude something like that quick, you're most likely want to err on the side of the prime factorization tree. Okay? All right? All right, so let's see what I have in my notes. So let me get a clean piece of paper and write out some of these so that we can kind of get an idea of what we're supposed to be doing. So 4 becomes 2 and 2. So that means the prime factorization is 4 is 2 times 2. Okay? If we have 18, we get 2 and 9 and 3 and 3. Okay? So that means 18 gives us 2 times 3 times 3. So to get the GCF, what we're going to do is circle the common factors. Okay, I'm not going to circle them because I'm going to put another number next to this in a second. So I'm just going to connect them. There's 1, 2 here and 1, 2 there. This 2 has no corresponding respective 2. So we're done. Okay? There's no 3 here. There's no 3 here. So we're done. That's it. So the GCF of 4 and 18 is equal to 2. That's it. We're done. Okay? So if I bring along another number like 24, I'm going to get 2 and 12, 2 and 6, 2 and 3. So here I get 2 times 2 times 2 times 3. Let me just double check. 6, 12, 24, yes. Okay, so now if we compare 18 and 24, let's get them both on the screen at the same time. Wait a second. That's, yeah. So this 2 matches. There's no other 2. This 3 matches. And that's it. So we're going to get the GCF of 18 and 24 is equal to 2 times 3. And that's going to be equal to 6. Okay? So if we did the GCF of 24 and 51, so 51 gets 3 and 17. So the 24 has no 17, but 24 has the 3. So we're looking for the common factors. They have to match 1 to 1 when we do this. Okay? So the GCF of 51, 24, it doesn't matter what order we put these two numbers, is 3. All right? So we can do a lot of problems like this. It's pretty obvious. This is what we're doing. We're creating a factor tree, whether it's prime factors or we create the list that I did in the first couple of minutes of the video, whatever the case may be. So we all cool this far? What about it? What about what I talked about so far? I don't want to delve into what I didn't talk about yet, but the parts I did talk about. I'm assuming everybody's cool on this. Let me see what we're doing on time here, because I don't have the time. Blah, 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 blah. Let me see here. Yeah, we're about 24 minutes. Okay. All right, so let me make sure I covered some of the stuff I wrote in my notes here. And just to throw off another one. Okay, so if I have 50, I have 2 and 25. And again, you have to know that things like this break down, or you're screwed. If you don't know that 25 is the same as 5 times 5, and this gets back to the 51 one again. If you don't know your division by rules, then you're not going to get the right prime factors. If you think this is 2 and 25, you're screwed. You're done. That's the end of it. You're not going to get the right answer. Okay, so if you have 50 and 100, okay, this becomes 2 and 50. This becomes 2 and 25. And this becomes 5 and 5. So this becomes 2 times 5 times 5. And this becomes 2 times 2 times 5 times 5. So we have 2's in both of these. 5, that 5 matches that 5, and this 5 matches that 5. So our greatest common factor, remember all of these are factors, including the original number. Our greatest common factor is 50, because we get 2 times 5 times 5. They're the ones we drew arrows again. Again, in your guys' cases, I would suggest you circle them, or you line the two of them up next to each other. So if you have 2 times 5 times 5, keep them in order, and 2 times 2 times 5 times 5. You can see this matches, that matches, that matches. Okay? And I'm off the screen again. Wait a second. Right? So you can see that matches, that matches. If you line them up next to each other. Or just circle them as you're going back and forth, circle them. Because normally you're not going to reuse the problem. That's just where you are. All right, so now we're going to talk about multiples. And this is where it gets ugly, because I already wrote out some of the factor trees here. So again, if I have the number 5, then the multiples are 5, 10, 15, 20. And the multiples, say 10, would be 10, 20, 30, and 40. And so on, dot, 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 dot. Okay, and this is the problem with the non-prime factorization, because we're going to move into the LCM now. Okay? So I think we're done with GCF. This is actually, I'm going to return at the end, because there's a way to do both of them simultaneously that we're going to get into, I hope. I wish it was shorter, but nonetheless. So if I want the least common multiple of 3, let me write it out in the terminology. The LCM of 3, 4. Okay? What I usually do is I take the larger number, and I just start writing its multiples. 4, 8, 12, 16, 20, 25. Wait, did I do that right? No, I didn't. 24. Okay, be careful. And that's the danger of this technique. So on both techniques, it's the division by stuff and making sure you know the factors. This technique gets too tedious and sloppy. So there's that. Because you can all of a sudden get off. If I say 29, I would have wrote, 25, I may have written 29. So at various points, you have to double check that this makes sense. So that's one thing. The other is, how long do I write this for? Okay, we don't know the answer to that. There's no way to determine that. So then I'm going to take the smaller number and just start writing multiples of that. And again, it's the same problem. I have to make sure I'm doing the multiples. And I don't know how many to write. So I'm going to write enough to go across the page. And normally I would leave a space here, because if I can't find the answer, I have to keep writing more on both columns. 18, 21, 24, so on. So we're looking for the least common multiple. In other words, which multiple is common to both of them? That's the smallest. It doesn't mean which multiple occurs the least. It's not a frequency question. It's the same as the greatest common factor. In this case, instead of least, we should really look at smallest. The smallest common factor is another way to look at it. All right? So which is the smallest common factor to both of these? It turns out to be 12. There's no other factor in both of these that matches up that's smaller. There's no 4 or 8 over here, and there's no 3, 6, or 9 there. So then the LCM of 3, 4 is equal to 12. And by the way, this is one way if you do have extra time, getting back to Leo's question, which way do you choose? Well, you know what? If you have extra time, do it both ways. But normally you don't. On something like this is that you have a minute and a half to answer a question. A lot of kids don't even finish the test, no less to go back to problems to double check them. So you really want to be on your toes in this is that. In fact, you want to be writing these lists neatly and taking your time. Because you're better off spending 2 minutes than spending a minute and a half and getting the answer wrong, and then having to go back and spend another minute and a half and 2 minutes. So instead of spending 2 minutes, when you say, oh, well, I went overboard 30 seconds. But pacing is the problem. Because if you make a mistake, you may do double and triple the time than if you just took your time and wrote everything out properly. So I'm a big person in writing stuff out and not just scribbling stuff out. You know what's cool? Somebody says, here's a problem, go! You know, and there's a clock going, then everybody's just doing it and you're going to be sloppy. You're going to write neat, but you still have to figure out your pacing. So what you want to do first in your strategy of your test-taking skills is just work on getting the right answer. You know, it doesn't matter how fast you do it, but if the answer's wrong and you keep getting every question wrong, it doesn't matter how fast you did it because you're getting a damn 0 on the test. So first of all, what you want to do is just go through and get all the answers. Try to understand all the little topics, the subtopics, all the nuances, all the different rules. Just learn the math, learn the ELA, whatever the case may be on your test. Then as you're doing that, then move into harder problems and still just try to learn them. Knowing how to do LCM is great, but if you have a word problem, you may not even know you need to use LCM. So there's a few levels and yin and yang that needs to happen through all this, right? So it's not a cakewalk. It's not easy peasy. It's not enough to say, oh, I know GCF now, I know LCM now. No, you have to be able to apply it as well, all right? And that's your juggle with the test. So learn the things, first of all. You're better off not answering all the questions, but answer the ones you answered right, than just zooming through everything and get every single one wrong. Or randomly you might get some right, or just you might know half of them and the other half you don't. You want to not be a slowpoke, but you want to figure out pacing yourself. So once you learn how to answer all the subtopics, then you want to start teaching yourself how to start pacing yourself. How can I take less time? How can I optimize this? What's a faster way to do this? If I observe the problem, does anything leap out at me mathematically? Stuff like that. All right? And it gets back to your mathematical mastery, including with the ELA part. And that's part of studying and prep. Okay? And it's not teaching to the test. It's not learning to the test. It's a skill like anything else. If your teacher's going to stand there and teach you square root, then they need to teach you all the other parts that are interrelated to square root, including what to do when you see a word problem. You know, everything in life is not easy peasy. So, you know, if you get a job and you have a complex problem where you have to build a building or something, you can't say, oh, it's hard. No, you got to solve the problem, all right? So, and this is part of your toolkit. You have a toolkit, you have a tool belt, and you're sticking all these little things. That's why people say, like, what is algebra for? What do I need to take chemistry? All this other stuff. Yeah, there's truth to that. But the other side of the coin is, as you solve more problems, even not directly related ones, you're teaching yourself and you're learning how to divide and conquer a problem, rip it apart and build it back up, and how to take one thing and work from different directions, and how to interrelate with people, or just negotiate in your own brain. How do I attack this problem? So that when you get to the harder problems, like how to build a building or something like that, you got all those kind of things figured out, and you have discipline in doing it. And it's not just rigor. It's not like, oh, let me take a sample test. Let me answer all the questions in the SHSAT, and I'll just figure out which ones I get right or wrong, and I'm just going to move on to the next test. No, that's a stupid, idiotic strategy. What you need to do is figure out why you got the ones wrong you got. Okay? There's also people who sit down and I even see this on some of the stuff, like the SAT. If I think I passed this the other day, the thing said, take the test and figure out what you get wrong. No, don't take the test and figure out what you're wrong. Learn the stuff first, then take the test. There's a whole iteration process that people are throwing out the window. Because once you take the test, I'm talking about the sample really here, there's no other sample to take. You already took it. Now, could you retake it and get a better score on what you learned? Yes, that's possible. But what, are you going to take it 5 times? And I know people have done that. You don't take the same sample test 5 times. Okay, that's ludicrous. All right? So, all right. I'm spending a lot of time getting passionate here. So that's how we're doing something like this. All right? So, so we can go through some of the same numbers. So let's focus on the because I can go through all the examples with 18 and 24 and so on, and we're just going to find that smallest number using this same technique. So let's do some with the factor trees. So let me get another piece of paper again. So let's just take a simple one. So if we have 3, we just end up with 3. And if we have 4, we get 2 and 2. All right? Because actually there's not even a factor tree here. Just 3 is 3. So with LCM, what we're looking at is all the leaves at the bottom. Right? With the GCF, we matched them up 1 to 1. All right? So we're going to get the least common multiple. Again, think least common denominator. Think denominator. Again, you have the 1/3 plus the 1/4. And you're trying to struggle to get that in there. Just keep that notion in your mind. So what we're going to do is just multiply this. We have 3 times 2 times 2. So we get 6, that's equal to 12. So if you keep this 1/3, because we're going to end up with something over 12 plus something else, x2 over 12, to actually get some coherent number, like 7/12 at the end. I think some of you know that would be the answer to that. All right? So that's all we're going to be doing here. So let me follow where I had some of the other examples. So if we have 8, we get 2 and 4 and 2 and 2. If we have 14, we get 2 and 7. All right? So now there's a slight gotcha with this. And here's where it gets ugly and kind of processing it. We said we're going to list them all, but if there's duplicates, in other words, there's 1, 2 here, but there's 1, 2, 3 2s in this case. All right? So what we're going to do is write out every unique factor. So what are the different factors here? There's 2 and there's 7. All right? So we're going to take the list where there's the most of them. There's 1 here and 3 here. So we're going to do 2 times 2 times 2. And there's 1 7 here at all. So times 7. So we're going to get 4 times 8. Wait, did I do that right? 4 and 18. No, I meant 18, but in this case it would be 56 then. So I was using 18, which is 2 and 9. I wrote out some examples just so I didn't screw up like this. So we have 2, 2, 2, and 2, 3, 3. So we're going to take us the 3 2s from here and the 2 from there. I'm still screwing up because I wanted to use the number 4. Here, let me do this over with 4 and 18. I just want to follow the things that I did. So we get 2 and 2, and 18 is 2 and 9, and 3 and 3. I laid out a bunch of problems so that, so again, this is 2 times 2, and this is 2 times 3 times 3. So the unique factors is 2 and 3, right? So we're going to find which one has the most 2's, that's this. And which one has the most 3's, that's this. So if we multiply all those out, we get 36. Okay? 3 times 3 is 9, times 2 is 18, times 2 is 36. By the way, this is a little cute thing that multiplying by 4, because 4 is the same as 2 times 2. So if we have any number, if we double it and then double it again, we can get there. So if I have 9 and I double it, I get 18. If I double that, I get 36. So I can multiply something by 4 just by doubling it twice. I can also take a number and divide it by 4 by going backwards. 18 divided by 2, 36 divided by 2 is 18, divided by 2 is 9. And you can often do even larger numbers in your head by doing this. So I have 125, double it is 250, double it is 500. Same if I have 500 divided by 4, if I half it, I get 250, I half it again, I get 125. So this kind of stuff you can do in your head. But again, I would advise you guys, because this is number sense, I would advise you guys to actually do this, write it out on the test, use your scrap paper wisely, no matter which standardized test you're checking here or not. Okay? All right, so we get 36. Where's the other problem I had? So we're there. So if I have the LCM of 18 and 24, I'm going to keep writing this out because we can't see all the pages. So this is 2 times 3 times 3. This becomes 2 and 12. This becomes 2 and 6. This becomes 2 and 3. So this becomes 2 times 2 times 2 times 3. Okay, did I do that right? That's 9, 18. This is 6, 12, 24, yes. Okay? So the unique ones, we have 2 and we have 3. So from each one, the most 2's is from here. So we're going to have 2 times 2. Wait, it's falling off the screen. 2 times 2 times 2. Okay? And this one has 2 3's. So times 3 times 3. So we're writing the longest list of each unique factor. In this case, we only have a small number of factors. Right? We can have any prime number at the end of these trees. So let's just work backwards. 3 times 3 is 9, times 2 is 18, times 2 is 36, times 2 should be 72. Okay? So this is doing LCM using that. Okay? And let's do another one using 24 and 51. So we know this is 3 and 17. All right? So that one's just done. So we're going to ignore this for that. So we're going to compare these two now. So our factors now are 2, 3, and 17. Right? Well, there's 3 2's from this. So we're not going to take the 2's from the 51. We're going to take it here. So we have 2 times 2 times 2. There's 1 3 here and 1 3 here, so it doesn't matter which one we take it from. And there's only 1 17. So that's going to be it. Sorry, there was another multiply here. So we have 2 times 2 is 4, times 2 is 8, times this is 24, times 17. If we do 24 times 17, we get 8, 2, 14, 15, 16, and then 4, 2, and we get 8, 0, we get 408. So the LCM of 24 and 51 equals 408. Assuming I did that math right. Yes, I have that written in my answer here. All right? So again, we get a nasty number here. The least common multiple. All right? So if I had 124 plus, again, if you think denominator, plus 1 over 51, I'm going to end up with 408s. And again, this could be a subtraction. And again, LCM is not always used just for doing a division. Okay, it's not always used just for doing a denominator, rather. Sorry, I meant. Okay? All right, so Leo, if you're still there, or anybody else, does anybody else have any questions? I'm seeing 2 viewers at the moment. So does anybody have any questions? Well, I'm going to take something to drink. We're not done. So we're 45 minutes. So now this is the part where everybody starts getting confused, by the way, too, because we have all this prime factorization stuff, and it's kind of getting confusing. Because I can tell you the greatest common factor looks for the common factors, right? But this does too, just the longest string of them. So when GCF, we're matching it 1 to 1. Remember we circled it, but we drew those lines from 1 to 1? So in the GCF, we're looking for 1 to 1 matches. We're not looking for all the unique factors in GCF. We're only looking for the factors that have pairs, and a different kind of factor pair. We're not talking about where I do 1, 2, 3, 6, 12, and all that stuff. Those are different factor pairs. We're just looking for pairs of factors that match up, that are the same factor for the both numbers. And we're not going to include the factors that are not part of that. All right? And the least common, and again, remember the GCF turns out to be smaller than the 2 numbers. In the LCM, the answer is either equal to one of the numbers or equal to the larger number, or it's larger than both of them. All right? Because you're getting a multiplier. We can see that when we have the 1/3 and the 1/4 case, or this case, we've got this humongo number. Okay, and this gets tricky because how do you check that? You check it by making sure your factor tree is right. Okay? And sometimes, by the way, and Leo, here's another quick way to do this, especially when we talk about denominators. And again, this depends on your mathematical prowess. If I have a third plus a fourth, do not do the LCM. Just multiply the 2 of them. A lot of us are used to something like this. We can do this in our head. Okay? If I have a half, if I have something over 2 plus something over 10, we know it's just a multiplier of 5. Okay, don't try to do this. But normally when you have denominators, one way to do it is just multiply them. Okay, if nothing leaps out at you, just make this 20ths. Okay? Just make it 20ths. So by the way, on a test like the SHSAT or any of these, they're going to ask you an LCM question directly. They might ask you, what's the LCM of these 2 numbers? Okay? Another thing they may do is they may give you a word problem that you have to solve and use the LCM, where it's strictly an LCM word problem. Or they might give you a more involved multi-step word problem, where maybe in the 3rd step of this multi-step problem, you'll finally use the LCM. So you have to know how to use it. So it goes from raw, like can you show us you know how to do an LCM, to here's a word problem, can you figure out you're supposed to do an LCM? And then here's something more deeper that's going on there. So sometimes when you're doing those deeper problems, because sometimes you have to match an A, B, C, D, or answer, right? So if you're doing a deeper problem, just sometimes it's worth using the uglier number, and sometimes it's not. But again, a lot of this is a judgment call. It's just how familiar are you with math? How comfortable are you with a nasty number? Because one thing is that the denominator gets larger. Normally you have larger numerators too then. And if you have to add them, the capability of making a mistake is higher. And one thing I like to do, which also doesn't work, is to take a fraction, like 30, 40ths. Sometimes it's worth simplifying that, and sometimes it's not. And you have to understand the greater picture of the word problem or whatever you have at the time to decide whether that makes sense or not. Because it's either think, oh, I should simplify everything right away. But if this turns out if this is relating to a percent problem, where really the goal is to figure out that you need to get the opposite, 70%, then mapping this to 3/4 is not going to help you. Okay? And I guess I should be saying 25% here. All right, so you have to figure out the full context and do this live. And again, this is why these tests are hard, and that's what's going on here. They're trying to figure out, they're not just asking you 1 + 1, they're trying to see, can you figure out these things? Do you have the rigor? Do you have the discipline? Do you have the creative intelligence to pursue this and do it in a speedy fashion? And some people can argue, oh, standard test doesn't prove anything and so on. There's a lot of truth to that, but there's also truth to the other side of it. Because what's the alternative? If you don't do this, what's the alternative? And it's a political debate going on now. I didn't really mean to tie into here, but if we talk about using the state test measures something else that the SHSAT or the SAT or something else doesn't measure. And at the end of the day, there's no real way to measure it. Because people, oh, it's a multiple choice test. There's problems with multiple choice tests. Yes, there is problems with multiple choice tests. But what's the alternative? That everybody hand writes it out and you have people grading these problems for months? No, that has to be done in an efficient fashion as well. Okay? All right, so let me check my notes. Let's see, this page 4. So again, remember to distinguish this notion of, whether we're going from a part to a whole or a whole to a part when we're talking about factors and so on. And it gets confusing because when you go through a multiple, going backwards, some of those turn out to be factors as well. So instead of trying to take GCF and LCM literally, just try to focus on the concept. If anybody saw my lightning round on angles the other day, and I have to do other parts of that, by the way, I was least concerned that I mentioned something like when you do this, this turns out to be this, and these are called vertical angles, and there's other things called adjacent and so on. That's all fine and dandy because sometimes you need to know what things are called. But it's also important just to know that this angle would be that angle, no matter what you call it. Just get that notion cognitively as a mental cognitive issue, a concept. You need to get that down. Okay, and then worry about what it's called. Because you can know this is called vertical angles and not know what they mean. So the point is not to just recite GCF and go through the procedure and recite LCM and go through the procedure. It's how do I use this bugger? First of all, when I'm asked. But what if I'm not asked? Do I know when to pop it into a problem or whatever? Okay, all right, so what I'm going to show you is another way to actually do both of these simultaneously. Oh yeah, booyah. All right, so let me start off with a simple example. If I have 9 and 6, okay, what I'm going to do is I'm going to put any divisor of both of these on the outside of here. So 2 doesn't work because it goes into 6 but not into 9. So let's put 3 here. Okay, and basically we're going to do an upside down division. So 3 goes into here 3 times and 3 goes into here 2 times. Okay, and when we continue this until we end up with only prime numbers. Aha! See, these buggers keep coming back in. Okay, so in this example, we're done. That's the end of it. There's no other common factor to both of these that can be divided. Okay, so what we're going to do is draw an L. And we're drawing L because the least common multiple of 9 and 6 equals everything in that line. 3 times 3 times 2. Which is 9 is equal to 18. Woohoo! Okay, this is cool. This is awesome. This is awesome. And the greatest common factor of 9 and 6 is only this line here. So the only thing appearing in this case is 3. Okay, let's say that again. You're going to go through this table. You're going to put an L here. And when you get used to this, you don't need to do the L anymore. The L is the least common multiple ones because there's an L. That can't be hard to remember. And the other one is just the straight up and down, the vertical line. Any factors along here is the GCF. Okay? So we can compute both of these simultaneously. And it's kind of, if you think about it, it's really doing the factor tree in a different way. Okay? You know, the trees we did before, all this stuff? It's a different visual, spatial relationship that we're creating of the factor tree. We're just doing it in a different way. Okay? And then depending on whether the question is asking for this or this, you can either write them both out or just compute the one you need. So now really the only problem is making sure you do your divisions right and making sure you list out what's on the L and what's on this line properly. Okay? So let's do another one. Let's see where we're at here. So if I do 12 and 36, all right? So I'm going to start with one of the factors. I'm going to start with 3. Okay, 3 into 12 goes 4 times. 3 into here goes 12 times. Okay, is there anything else I can do? Yeah, I can go in one more time by 4. I end up with 1 and 3. I'm only ending up with prime numbers, so I'm done. I am done. So my LCM is going to be this. 3 times 4 times 1, so we don't really need that, times 3. So we got 3 times 4 is 12, times 3, we get 36. Okay? The GCF is just this part. So it's 3 times 4, and that's equal to 12. Dude, and think it through. What's the least common factor here? That can do 36 is 12. And the least common multiple turns out to be the larger number. Remember I mentioned that before, maybe 10 minutes ago in the video? Okay? Sometimes it can be the larger number. So I was talking about the GCF, okay, is at least as small as both of the numbers, and the LCM is at least as large as the larger number. Meaning it can be larger, and meaning this one can be smaller. Again, that's just kind of a fact of it. You don't really have to memorize that. There's other identities and so on that also happen with this. So let's do another one. 18 and 12. So I can do 2, and I get 9 and 6, right? I can do divided into 3, and I got 3 and 2. So I'm done. I'm done. So the LCM equals 2 times 3 times 3 times 2. That's 9, 18, that's equal to 36. And the GCF equals 2 times 3 equals 6. And by the way, we could have done this another way. If I do the 18 and the 12 here, and again, it doesn't matter which order we put these in, okay? If I just straight out started with 6, I get 3 and 4, right? No, sorry, I get 3 and 2, right? So be careful. So I'm only done with primes here. So my LCM here is equal to 6 times 3 times 2. That's 18 times 2, that's 36. Guess what? It's the same number here. And my GCF is just that number there. It's 6, and guess what? It's the same number there. So like how we do the factor tree, it kind of really doesn't matter. It kind of really doesn't matter. So let's do the other one I've been doing. If I have 50 and 100, again, we could do this in multiple steps. But if I just start with 50, that's 1, right? And and 2. And that's it, I'm done. So my LCM is 50 times 2. That's 100. So again, here's another one where it's equal to the larger number. And my GCF equals 50. My greatest common factor. What factor is the same as turns out to be equal to that number? And I'm done. That's it. That's it. All right? So, did I able to pull this off in less than an hour? Literally an hour. Yeah! Okay. All right, does anybody have any questions? So hopefully this was helpful. It's probably still confusing. It's worth at least using this last technique to double check it, because you want to be comfortable when you get to the test with these concepts. Okay? And you want to be able to solve problems. So all I'm trying to do at this point is get you through the robotics and the procedure, and to have some understanding of a multiple, some understanding of a factor, some understanding of what's kind of going on here, and then there's the rules. So remember, the greatest common factor is picking out one-to-one the common factors of the prime factorization tree. Okay? LCM is picking out all the unique factors and picking the largest group of factors from one number or the other and multiplying them out. All right? And then this other technique is kind of a backdoorish way to do them both at the same time. And again, if you just know you need GCF, you just use the left line. If you need LCM, you do both. And by the way, if you notice, in all the ones I did, that some of the beginning part of a lot of these is the same. So you can almost just do the GCF and multiply the other part on it. It depends what you're doing. Okay, there's no right or wrong way here. And again, it's contextual. It is contextual. So, thumbs up, thumbs down. Please like the video. Please subscribe to my channel. There's tons of other material. This is just one topic of so many. We actually didn't cover the usage parts of this, which is where it is. We cover one usage, which is when you're trying to get a common denominator. But it also comes in handy, like if I have 30 brownies and I'm trying to split it across 5 people or something like that. How do I have to factor this out? Or if something happens every X days and something else happens every, if something happens, a classic case might be like, I'm going to tutor somebody in math every 3 days, and I'm going to tutor somebody else in the ELA every 5 days. Okay? So for a while, I don't have a conflict. Let's say I only tutor on Wednesdays. Well, that can't be true, but let's say I only tutor at 5 o'clock. So if I start doing today, and how long will it be? Will I have a conflict where I have the 2 kids at the same time? And do I have a way to schedule that, right? So what you have to do is try to figure it out of 3 and 5, what that might be, right? So that becomes the word problem. Greg has to tutor a kid in math every 3 days, and he has to tutor somebody else in English every 5 days. He does this only at 5 o'clock. How often will it be true that he has to reschedule one of the kids? Okay, so that's the kind of a problem there, and we're going to be looking at 15, right? So there we go. All right, I'm sweating. My computer's sweating. It's raining out. So I'm just going to chill for a while. I might do an Ask Me Anything stream, guys. Please check out my other videos. There's tons of stuff. I have a whole ton of stuff on grade 7 math, grade 8 math, grade 9 math, how to take the SHSAT. Ask Me Anything questions on the SHSAT. There's some from last year that are up. I did an assessment, multiple assessments of this year's student handbook. I have a few videos up about how to do poetry, because it's true across the board. And poetry is one of the parts that a lot of kids just think are evil. And a lot of kids have problems with it. It's bad enough doing the math problems like this. It's bad enough doing reading comprehension questions. But the poetry is a killer. It just adds a second level in the direction onto stuff. And it just bends a lot of people's minds out of shape. So I have at least 3 videos. Some are over an hour long, where I'm analyzing a whole bunch of stuff. I think I even did one on this current year's SHSAT. I'm thinking fireworks, something had to do with fireworks. Or maybe I'm thinking of something totally different. Again, that's a question from this year, so actually I would probably hold off on that. But the kind of question is hard enough that maybe it's something to delve into. But again, I have 2 or 3 other streams where I talk about poetry. And it really doesn't matter what grade level you're doing this at. In fact, I suggest students start at earlier grade levels and build yourself up to there. I think this is an unsung hero approach to doing some of this, because everybody's worried about what's the grade 9 SHSAT? What are the advanced topics on grade 8? Dude, if you didn't get 100 on the New York State test in math, then you need to sit down and still work on your basic understanding problems, no less the SHSAT problems side of it. Okay, right? All right. Yeah. So I'm starting to ramble. I'm going to peace out myself. Take it easy, people, and please like and subscribe. Thank you, and goodbye.